All right, so we're going to talk about work, energy, and power today. So good science stuff. This stuff, I can relate to this stuff. This is right up my alley here. So we're talking about work. We're talking about force times distance. When we were talking about like the inclined plane, and if I'm applying that 20 Newton force up an inclined plane of 10 meters, that's my, multiply those two together, that's going to be my work. When you measure work, you measure it in joules. Joule is the SI term for work. So we're talking about 1 joule is equal to 1 Newton times 1 meter, or 1 Newton meter. There, that person just did some work lifting that red thing, whatever that is. A 50-pound red ball, 4 feet in 5 seconds. Okay? So he lifts that, 50 pounds, 4 feet, 5 seconds. This is, okay. So, guess what? We were just talking about joules, and that's all SI term. So, everything they gave us was in English terms. So, we got to do some conversions here. So, here's a conversion. 1 pound is 4.45 newtons. 1 foot is 0.305 meters. Seconds, fortunately, we don't have to convert. So if we want to change 50 pounds to newtons, it's going to be 223. Take the 50 times 445. If we want to change 4 feet into meters, 1.22 meters. All right, so now we've got 223 newtons, 1.22 meters. Solving for work, we put those numbers in, and we get 271 joules. All right, so if we're talking about energy, energy is simply the ability to do work. So the work we just talked about, we need the energy to do it. So we can be talking about different kinds of things. A roller coaster uses energy, as it goes up, it's up high, it has potential energy, and then it moves, or it's mechanical energy. You've got NASA, and they talk about a solar sail or fuel cells. Those are all examples of energy. There are different forms of energy. One of the main categories that we classify energy into, one of those is known as potential energy. That's usually known as, a lot of times they call it, like if we're talking about gravity, we're talking about energy of position. So an object that's high up in the air has more potential energy because as it falls, it can do some work, it can do something. But it doesn't just have to be gravitational energy. It can also be stored energy, like energy in coal or energy in gasoline. Gasoline has potential energy. If I light it on fire, I get a lot of heat, and I can use that to do some work. So, they all have potential energy. One of the other, if we don't have potential, we very likely might have kinetic energy. Kinetic energy is energy of motion. When something is moving, it has kinetic energy. So anytime you have something moving, those wind turbines, when those things are moving, they've got kinetic energy. We can then take that kinetic energy and change it into something else that we want to use. But we've got that kinetic energy. So they show water moving, they show space shuttle, so on. Kinetic energy, okay? Can come, it says occurs anywhere from atomic level to that of a whole organism. So the last one, the light bulb, we're talking about electrons moving. So that would be more at the atomic level. All of those energies, we transfer those things back and forth a lot, okay? So for instance, you eat food, your body takes that food, digests it, that's chemical energy in the food, you convert it into movement, into mechanical energy, for you to be able to go do stuff. Or you take radiant energy like the sun, and we convert that into something else, which I don't really know what that is. What's that picture, guys? The person holding something.
A bat? Or like the one below?
No, this one, right here. What is it? I don't know what that is.
She's playing baseball, isn't she?
She's playing baseball?
No, the top one.
I'm not looking at the top one. The top one is like lacrosse or something. But What is she holding here? I don't know. I don't know what that is. Anyway, radiant energy. Obviously, we can take the sun and we can use it for heat. We can use it to change solar. Use it on solar panels and changing electricity, things like that. Electrical energy. You might get electricity. Turn on your oven, cook your turkey, have a nice Thanksgiving meal. Okay. So once again, just to review, here's a lot of our renewable resources that we have: biomass, hydropower, geothermal, wind, solar. Those are ones that we have. And we need to be able to convert these. We've got to be able to change those. Non-renewable being coal, natural gas, petroleum, and uranium. Okay? There's a law in chemistry called the law of conservation of energy, which says that energy can't be created or destroyed, but only changed. We can change it from one form of something to something else. We can't create it. We can't get rid of it. It's there. Sometimes it's not useful energy, but it is there. And when we change it from one thing to the other, we've got this energy conversion going on, we can figure out how much efficiency we have. The better off we are in converting that energy into something we want to use, the better efficiency we have. A car engine is not real efficient because it has a lot of wasted energy. So when you burn gasoline, there's a lot of energy in there. Well, we're only getting maybe 30, 40% of that energy to move the car, which is really what we want. And the rest of that is wasted. Okay? So, in a car engine, think about how hot a car engine gets. All of that is wasted energy because we are not using that heat to do any work. All we're doing is just losing it. So that's wasted energy. That's not efficiency. That wasted or loss of energy is known as entropy. Entropy, physics kind of predicts the end of the universe at some point because eventually there's going to be, all of this energy will become what we call entropy, and we can't use it. It becomes a non-usable form. We can't get any work out of it, and when that happens, nothing will happen anymore. You can't do anything. Now, don't worry. That won't happen in your lifetime or any of your grandchildren's lifetimes or any time for another few million, billion years. But, eventually all of our energy gets kind of used and it now becomes unuseful energy down the road. But if we want to figure out efficiency, we simply figure out, well, how much did I put in? What energy did I put in and how much did I get out? And output over input over times 100 gives me my percent efficiency. Higher the percent efficiency, the better off we are. We would like to have, you hear like gas furnaces, a lot of those are 98% efficient. So they're taking that natural gas and 98% of it is being useful heat that you use to heat your house. And 2% is probably lost to the outside, that you lose outside. So that's kind of what we want to do is try to find good, efficient uses of converting energy. Here's some examples of energy conversion. You might start with a fossil fuel, which is chemical energy. You might change it to heat. Maybe we take that heat and we get mechanical energy, and from that maybe electrical energy. So you could burn coal, for instance, get the heat from the coal, use that to move something and create electricity. That's what we're talking about. Or solar cells, we can go directly from sunlight to electrical. Wind turbines go from kinetic to mechanical to electrical. Or hydroelectric, gravitational potential. In other words, gravity's pulling the water down. We use that to move a turbine. That's mechanical. We create electricity. Or nuclear to heat to mechanical to electrical. Okay. If you've got a car, we've got chemical energy. We put gasoline in the car, we get chemical energy. From that, we get mechanical energy and heat. Now, which one of those is good? Which one of those do we want? We want mechanical. I would rather have a car engine that didn't get hot. If I could turn it all into mechanical and not waste that heat, I would get more miles to the gallon. And I wouldn't have to spend. What is it now? $3.30 a gallon or something? Just went up like 15 cents or something. 13 cents? I don't know. All right, so what are some current energy concerns? What are some issues that we have? Well, obviously, we have pollution we have to worry about. You know, right now with all the cars and everything, you know, especially if you're in a big city like New York or Los Angeles, you have pollution, you have depletion. Eventually, we're going to run out. We have dependency. We are dependent on this, and right now, like for instance, oil. We are dependent on a lot of oil, and we get most of that from other countries, and that's not always a good situation. And then there's cost. Okay, so take a look just over at the chart for a second and see what percent we get from those different sources. And you can see that most of our energy comes from petroleum, natural gas, and coal. You know, that's what, about 80, a little over 80%, 83, 4%. That's where we get it. Those are all fossil fuels. You know, we really probably, at least in the near future, or down the road anyway, we need to start moving into some of those other ones. Some of them on the left-hand side, biomass, hydropower, geothermal. You know, we need to up those percents so that we're not as dependent on some of the other things. So what roles do engineers have in energy? What, if you're an engineer, what might you be doing in this?
Increase efficiency.
Maybe you're working on a more efficient car or a more efficient way of taking heat energy and converting it to mechanical, or maybe you're coming up with a better way to create wind turbines. You know, I mean, there's all kinds of those things. Okay, so power, when we talk about power, we're talking about the rate at which we get work done. In other words, how fast do we do the work? So I could push this box up the inclined plane. That takes a certain amount of work. Somebody else might come along and run up the inclined plane pushing the box. Now, we both did the same amount of work, but one of us did it faster than the other. The one that did it faster takes more power. So the difference between work and power is basically the amount of time involved. So power is work divided by time. And when we're talking about power, we're going to measure it in watts. Measure how much work we got done per second. So 1 watt is equal to 1 joule of work per second. So we said a joule was a Newton times meter, force times distance. 1 watt is 1 joule per second. So that'd be force times distance divided by time, or seconds. So what are some different types of power? Well, we can have electrical power. We can have mechanical power. Mechanical meaning moving, you know, things that are moving. And they talk about linear or rotary. Linear meaning we can have something move forward, straight line, you know, forward, backwards, that would be linear. Rotary would be something that goes around in a circle. There's fluid power. You know, we have a lot of things are hydraulics or pneumatics. What's the difference between a hydraulic system and a pneumatic system?
Pneumatics uses gas and hydraulics uses water.
Yeah. So when we're talking about like hydraulic, we probably have some kind of liquid in there, maybe oil, maybe water, whatever. When we're talking about gas, we have maybe air, you know, something like that. Or pneumatic, we have air. All right, so here we're back to this ball, this 50-pound ball that we kind of just left sit there after a while. But we said we did this in 5 seconds. So we knew our work from before was 271 joules. Well, if we did it in 5 seconds, then our power is 54.3 joules per second, or what? Watts. Okay. Hey, there we go. We are done. Woohoo! Do you feel smarter now?